This video is about rate equations. You should already be able to describe the rate of a reaction and how it's affected by changes in concentration. And by the end of the video, you should also be able to calculate the final or initial conditions of the substance during a first or second order reaction, as well as calculating the rate constant or the time the reaction takes during the first or second order reaction. So the question in the video that we're going to try to explain by the end of the video is that N2O, or nitrous oxide, is used as an anesthetic, like laughing gas and maybe when you're getting your teeth done, and a propellant in aerosol spray cans. It breaks down into nitrogen and oxygen, which are normal components in the air. We want to know how quickly does it leave a system. So first, let's talk about first order reactions, where the rate depends on the concentration to a first power. You can write it in a rate expression where it's the negative because it's being used, change in concentration of that substance over time. Or you can write it as a rate law where rate equals K times the concentration of that substance to the first power, which we don't really write once. And if you rearrange those two equations combined, because they're both the same rate, you'll get something that's rearranged to this equation, which is found in your reference table. The natural log of that concentration at any time minus the natural log of that concentration at the initial time, that's what the 0 stands for initially at time 0, is equal to the negative rate constant times the time that it took to get to this concentration, the first concentration you have written. And so AT is concentration of the substance at any time t, and A0 is the initial concentration when the time is 0. The way we use it is like this example. The reaction of 2A makes B is a first order reaction, even though there's two of them. Remember that it has to do with rate, concentrations, and times in a experiment. Had a rate constant of 2.8 times 10 to the minus 2 per seconds at 80 degrees Celsius. How long did it take A to decrease from 0.88 molar to 0.14 molar? So we wanted to know how long it takes now, the time. And so what we could do is plug it into this equation knowing it's first order reaction. You have to make sure you're doing the final temperature, the final condition minus the initial. So the final condition is 0.14 and the initial is 0.88. So make sure you're plugging those in the correct order. And then we're going to divide by negative k to get t alone. So the negative k was negative 2.8 times 10 to the minus 2. So make sure you have that negative in there. And that gives you the time as 66 seconds. Notice the k was in per seconds, and that's why our time is in seconds. So it's telling us how quickly it's going to change in that concentration. Now, the only reason why you were able to do this is because you probably had done a series of other experiments where you knew it was first order, right? Let's try this again. This one says cyclopropane changes to propene in a first order reaction, where K is 7.8 times 10 to the minus 4 per second. If the initial concentration is 0.35, calculate the final concentration after 9.8 minutes. So we're going to use this first order equation again because it said it was first order. Also, the K had only one unit, so that's a big hint that it was first order. And this time we're going to be solving, instead of solving for T, we'll be solving for the initial concentration of cyclopropane. So this 8's 0. So we're going to put 0.35 in for the concentration at 9.8 minutes. Notice the minutes and the per seconds don't match. So I decided to change the minutes to seconds, 9.8 minutes times 60 seconds. I showed that here, but you don't have to show it like that. But I just wanted to make sure that we're clear that I'm changing the minutes to seconds so that it kind of corresponds to the K will cancel. And when I solved it, I got 0.22 molar. We're going to solve a lot of these equations, but one thing that you should be aware of is when you solve this, you're going to be multiplying the right side together and then adding the natural log of 0.35. If you have the natural log of x and you want to get x alone, you'll have to take the exponential of that question. So the E button on your calculator to undo the natural log. And so then another question might be like, now that we know what the concentration was initially, and we know what K is, find how long it takes to decrease from 0.75 to 0.05. This is a similar question as we did before. Since it's still first order, you can still plug it in, and I got 3,500 seconds. You can leave answers like this as 3,500 seconds. If you want to convert to minutes or hours, you could, but I see no reason to do that because you're just setting yourself up to make a possible mistake. First order reactions also have a half-life, or a time it takes for the concentration to decrease in half of its initial concentration. Because it's reacting at a same pace, it's kind of like half-lives we did in our nuclear unit, right? So you have a full solution at your initial, and then there's a time it takes for half of that to be reacted, and a time for another half, and a time for another half, and you can do this until there's no more particles to react. So what's the half-life of N2O5 if it decreases with a rate constant of 5.7 times 10 to the minus fourth? You might say, hey, I know I'm going to do a first order reaction, the natural log equation, and you can do any concentration. So like you can actually count up how many particles there are and then do the natural log of the half of that particles minus that. Or they've actually rearranged the equation for you to this particular other equation. So I'm just going to take this question to the next slide so we have some room. So this was the question. I can use the natural log of any concentration I want initially and half it. So if I did 2 concentrations, 2 molar, it would be 1 molar halfway through, right? Or 200, it would be 100 halfway through. And then I'm going to divide by the negative k, right, to get our time. But another thing is, if that's true, that could be also reduced to the natural log of 1/2, if you know anything about logs. And that means it's always going to be the same ratio, whether it was 200 and 100 or 1,000 and 500 or whatever. So there's actually another way of calculating this. You can use this T1/2 formula on your reference table that reduce the natural log part for you to 0.693. And therefore you can just divide by the negative k and you'll get the same answer we did before. So realize that you can either use the first order reaction or use the T1/2 equation that's on the reference table. And then how do you know the decomposition is first order? Well, the fact that the units of k were per seconds, there was only 1 unit in the denominator, I know it's going to be a first order reaction. This is also known as a y minus b equals mx formula, where it's an equation of a line. It's just rearranged here. You probably use y equals mx plus b, right? We just took the b over, then y-intercept. And so if I graphed just a versus time, it would have been a slope that's curved. If I take the natural log of a versus time, notice the slope comes out nice and perfectly straight. So that means that the slope is equal to the rate constant, or k, a constant rate slope or a constant value, right? If I did it inverse, it doesn't come out straight. So the straightest line is the one for this equation, is the one where the concentration is natural logged versus the time on the x-axis. And that means that you can find your k graphically. So in this example, it says, consider a process in which methyl isonitrile is converted to acetonitrile. And the first thing we notice is that if I can also do this in pressure instead of concentration. As I react it decreases over time, but it's not a straight line. So then we know it's going to be not zero order where it doesn't affect it. If I actually graph the natural log of it according to this equation, I can get a nice straight line instead of just the regular pressure. I'm taking the natural log. And that means that this is definitely a first order reaction, because anytime you take a natural log of the concentration or pressure and it comes out straight, it's a first order reaction. And then from that data, if I know what the slope is, using either a calculator or doing a change in concentration over a change in time in the natural log form, I can find what our rate constant was, because the slope is constant. Right? So using a graph, we can find that the k is a negative slope, right, because it's going down. That's why we negated the k, and it was at 5.1 times 10 to the minus 5. Now I know what k is, I can actually plot in any data I want. We're going to move over to second order reactions. So second order reactions means that the A is also decreasing versus time, because we're always looking at the reactant. And the reactant is raised to the second power. It happens twice as often, right? It affects the rate twice as often. So when we rearrange these equations, we actually get an inverse reaction. And that is also y minus b equals mx form. So what it's trying to say is, if you have a second order reaction, notice a square, it has a different rate law or rate equation, which is on your reference table, and therefore we have to graph different things. So instead of just graphing the A, which is the concentration of that substance versus time, which would be curvy, or a natural log, which in this case would be curvy because we're talking about a second order reaction. If we did the inverse of the concentration, we would get a straight line, and then its k would be equal to its slope. Notice again that this slope is now positive, and that's why the k is positive in the equation. So a second order reaction we can calculate graphically, or we can calculate with our regular calculators. Here's a question. A second order reaction with k equals 7 times 10 to the 9th per molar second at 23 degrees. Find the final concentration after 22 seconds. Its initial is 0.086. So we're going to use this second order equation because it was said it was second order. Also because the k units have 2 units on the denominator, so a little hint there. We're going to plug in their values appropriately. So this k is going to go in for that k. That time, it works out because it's seconds and seconds, so we're going to put that here. And it said they wanted the final, so that means the first A if this initial was 0.086, that's the second A we have here. So make sure you plug it in appropriately and then solve nice and slow. K times T, add the 1 divided by 0.0816, and then you have the inverse. So you have to take an inverse of that or cross multiply to get your concentration. Notice the concentration should go down because it's started at this concentration and we're reacting it over time. Here's another type of a question. Calculate the time it takes for this concentration to change from 0.6 to 0.42. Same thing, it's still the same reaction, so it's still second order. We're going to plug in the numbers appropriately, meaning that final minus initial order. Make sure you make the order in the right order. And the K stays the same because it's the same reaction. So this time we're solving for T. I'm going to solve this nice and slow, 1 over 0.42 minus 1 over 0.6. And then I'm going to divide by this K value to get our time. It doesn't take very much time for it to change in that small concentration, which is why we wouldn't be able to actually put it in our stopwatches, right? This is something you have to calculate either graphically or in your calculator in order to figure out how long it goes. You can also do it graphically. So again, if you know it's a reaction order, you can put in time as your x-axis and the concentration as your y-axis. If this turns out to be a straight line where your regression values are close to 1, that means that it was 0 order. It didn't affect the concentration, didn't affect how long it took. If you do it as a natural log, the yield still slightly looks kind of maybe curvy. You're not really sure yet. And it's not really straight, so that means it's probably not first order. So what we would do is instead graph inverse, and now all of a sudden it's nice and perfectly straight, which implies it's second order, which implies that you should be graphing an inverse. So again, from that you can find the slope, because the slope is constant now that you have a straight line, and that slope is equal to your rate constant. Notice that the slope is positive, which is why your rate constant is positive, and you're just grabbing it from your calculator or from your graph. Notice again that this is second order, so the K has 2 units in its denominator, molar second. Last thing we're going to talk about is zero order reactions, so they're pretty quick and easy. They're not dependent on the concentration, so you can write it as how the concentration affects the time, but you'll find out that this is constant. And so therefore when you write a rate law, it's rate equals Ka to the 0 power, which anything to the 0 power is 1, so the rate is equal to the rate constant. So when you graph it all the 3 ways, the inverse or second order reaction doesn't work. The natural log or first order reaction doesn't work. It worked when you just graphed A versus T. And so the K is the slope, which is constant, right, because it's a straight line. And therefore that is also equal to the rate, A over T, right? So just to summarize, this is the rate law. If it was 0, would give it an integrated rate law looks like something like this. You would be graphing A versus T. The slope would be negative K because the slope was going down. And you have a half-life, which is not on your reference table, so we're not going to really worry about too much. You have first orders, which are raised to the first power. They have a natural log equation. So you'd be graphing the natural log versus T to get a negative slope, because notice the negative in the equation. And then the T1/2 formula is on the reference table, so we are worrying about that. We'll be either using this, or it translates to T1/2 equals 0.693 over K if you're using a half equation. And then the second order means it's raised to the second power. We'll be doing an inverse in order to use your integrated rate law. It's the inverse of A versus T. If you're graphing it, the slope will come out positive. Notice that it's positive in the equation. And the T1/2 is a little slightly different because we have a different equation. Again, you can either use this T1/2 or you could use any concentration and then half it over time. So back to the question in the video, how long does an N2O leave the system? A plot of now natural log versus that time, it gives you a linear equation, so it means we have a first order reaction. And when you plotted it, it was K equals 0.00231 per seconds. So now that we know that it's a first order reaction, because I plotted it, and we know what the K is, because I plotted the slope, I can actually find out that not only is it first order, I can figure out what its half-life is. So the half-life equation on your reference table says take 0.693 and divide it by the K value. When I did that, I got 300 seconds, or 5 minutes, however you want to think of it. And that means that it takes about 5 minutes for a molar solution to leave your system. If you put more in, it might take a little longer because you'll have to go through multiple half-lives, right? Because what half-life means is not all of it's out of your system, but that half of it is out of your system. So whatever they put in, only half of it has left. Another 5 minutes later, another half is left. And that's why you slowly come out of a laughing gas. When you put under, you slowly come out of it. It doesn't immediately just turn off because it's a first order reaction. At this point, you should be able to calculate the final or initial conditions or a rate constant or time for a first order or second order reaction.